Hi, and welcome to Lecture 9. We'll see how well this works. New setup once again. This time we are talking about the derivative. We're continuing to talk about the derivative, but we're talking about the derivative today as a function. So we already know that the derivative, we talk about this as f prime at some number, but we've also talked about it where the number gets replaced by some arbitrary letter like a, where we don't really want to say for sure what we're going to be plugging into this derivative to calculate the instantaneous rate of change. But there's not much of a difference between plugging in some unspecified number a and thinking about plugging in the independent variable, that is x. The idea of what we're doing here is that we're thinking about the derivative, this f prime, as if it were a function. Well, it is really. We're given the function f, and then f prime becomes the derived function, the function that we get from f by taking this limit. So it's useful for us to think about what this f prime of x might be, and it is a limit. Actually, it's the same limit that we've seen before. Let's look at f prime of a, because that's a good thing to consider, to remember what that definition is. It's the limit as, we'll use the h form, h approaches 0 of f of a plus h minus f of a, all divided by h. Now, that's the definition. We're familiar with that. But what if I just replace a by x? That's legal. So if I do that, let's see what changes. The only thing that changes, limit as h goes to 0, f of a becomes x, x plus h, minus f of x, and all divided by h. So this is kind of stupid, but the whole idea here is that now there's a subtle difference. I'm thinking about f prime as a function of x, not just something that you calculate at various places. I think of calculating the instantaneous rate of change at every possible x. Okay, so that's an idea of what the derivative is. As a function. You might wonder, why aren't we using the other form? I've said so many times that I prefer the limit as x approaches a. Well, it's a little bit awkward when you're doing this, because if you start writing the limit as what happens, well, I can't use x approaching x. That makes no sense. So I've got to make up some other letter. So I've got to come up with something, let's say like q, the limit as q approaches x, and then you could do it. You could write f of q minus f of x over q minus x. But nobody ever does this. I mean, I suppose it could be done. It might be done once in a great while. But we're certainly not going to look at that when we're trying to get the derivative as a function of x. Then it's much more convenient to just do this. Doing otherwise is more confusing. You introduce this additional variable, which doesn't make a whole lot of sense. Okay, so this is what we're going to be doing. We're going to be calculating the derivative as a function. Now, for those of you who might have had calculus in a previous incarnation, please do not yet remember all of the rules for calculating derivatives by formulas. Right now, the point is to learn this definition of the derivative. This time it's expressed as in terms of this independent variable x. You need to know it in any of its incarnations. You need to know it also as the slope of the tangent line and so on. And to make life even more interesting, we're going to talk about different kinds of notation for it. But I guess before I do that, let me go ahead and do one problem this way. Let's calculate f prime of x. So our problem is find f prime of x, where f of x is given by something like, how about 1 over the square root of x? All right, so we're going to use the definition that we were just using for f prime of x, the h form. So f prime of x, according to the definition, is the limit. It's always a limit. The derivative is always a limit. This time that's h goes to 0 of f of x plus h minus f of x all over h. Now we just plug in, this is the limit as h goes to 0 of f of x plus h, means you replace x in the definition of f by x plus h. So this is going to be 1 over the square root of x plus h. And then you have to subtract f of x, which is nothing more than 1 over the square root of x, and then you divide that whole thing by h. All right, now how do we do this? Well, as usual, whenever we do a derivative, if you just check what happens as h goes to 0, bottom always goes to 0. This h goes to 0, leaving you with the square root of x on the bottom, 1 over square root of x minus 1 over square root of x. Yeah, it gets 0. So you've got 0 over 0. Bad news. You've got more work to do. What can you do here? Well, let's get a common denominator. That seems like a good plan when you have two fractions. So this is going to be the limit as h goes to 0 of the common denominator upstairs is going to be the product of those two things, square root of x plus h and square root of x. So I have to multiply those together. And this term I'm going to have to multiply by just the square root of x. And then I'll have minus. And then I'll have the second term where I have to multiply that by square root of x plus h. Well, this isn't a whole lot better, and in fact I've still got a 0 over 0 as h gets small. Oh no, I'm sorry, I left out the bottom part. This h, how do I deal with that? Well, this is an h over 1, so I could flip this bottom over and multiply by it, which means that I've got a 1 over h, so all that's going to do is it's going to put an h down here on the bottom. Okay, go through that yourselves to make sure that you can do this kind of computation. Get the common denominator upstairs, and then once you've got that common denominator, then deal with that fraction down below by flipping and multiplying. You'll see that the 1 goes up here, that doesn't change a thing, and then the h just slips down to multiply by all that stuff. Okay, how do I deal with this? It's still a 0 over 0 because this h is making the bottom 0, and here that h is going to 0, so we've got square root of x minus square root of x. Well, here's where we need that other trick where I'm going to multiply by the conjugate. So I multiply by the square root of x plus the square root of x plus h. And of course, if I do it to the top, I have to also do it to the bottom, or else I would change the problem. Now, the nice thing about multiplying by the conjugate is that you end up with the square of the first term minus the square of the second term, and with radicals all over the place, those radicals are going to go away when you square them. So this becomes nothing more than the limit as h goes to 0 of the first thing squared, which is x, because you lose the radical when you square it, minus the square of the second thing. And make sure you put parentheses around it because it's that whole thing that's being subtracted, x plus h. That's this squared minus that squared after you multiply through. And then you have to divide that by, unfortunately, there's not much that happens that's good downstairs, so you're just going to have to keep x plus h under the radical times square root of x times h times that mess, square root of x plus square root of x plus h. But fortunately, there's something good that happens. The x's are going to cancel, leaving you with minus h. So you're going to have minus h upstairs, And folks, please don't get tempted to multiply out this mess down below. Leave it. You'll see that if you multiplied it out, it wouldn't help you at all. And sometimes you have to factor it back out again. So just leave it, because probably it'll be fine. So here it is again. But the difference is that now the h's are going to cancel. And then you can let h go to 0 and nothing bad happens. The numerator just becomes -1. And the denominator, well, let's see. You've got a square root of x plus h, but h goes to 0, so it's just square root of x, times square root of x. Well, that's nice. That's just x. Radicals go away. H is already canceled. And here we have, in the parentheses, square root of x plus, here's another term where h goes to 0, square root of x. So you got 2 square roots of x. So if you want to get fancy, you can simplify this thing as -1/2 times, in the denominator you could have x to the 3/2, x to the 1, x to the 1/2, x to the 3/2. So if you want to get real fancy, you write it as x to the -3/2, just to impress people with your ability to manipulate exponents. So that's it for one big, long, nasty problem. All right, let's go back to talking about the derivative as a function. And, oh yeah, this is the derivative of the function 1 over square root of x. This was the original function f of x. And looking at the derivative, the slope of the tangent line at all points x all at once, we were able to see that it's this. Okay? There are a couple of other notations I wanted to point out. One that comes up very, very often is called the Leibniz notation. And it comes from the idea that the derivative is really based on this delta y over delta x, except this is just the average rate of change, as you know. But we could take this to the limit as delta x goes to 0. I mean, that's what happens with all of these derivatives, you know, where you have f prime of a or whatever. It's always a limit as h goes to 0, or a limit as x goes to a. But in either case, whether it's x getting close to a or h getting close to 0, it's a delta x that's getting smaller and smaller in whichever form you're looking at it. So if you're looking at the difference quotient and letting that limit, letting that delta x go to 0, this is another way of thinking of the derivative. It's very, very practical in terms of real-world problems, as we'll see later in the semester, and in your future experience with math. So there's a special notation for this. The derivative in this form is not written functionally, but it's written this way: dy divided by dx. And the idea is that we call this dy dx, we call this the derivative of y with respect to x. This focuses on the idea that when you've got y as a dependent variable based upon x, then this expression tells you explicitly what the change in y is with respect to x. So we can see the dependent variable and the independent variable explicitly when we use this notation. Now, there aren't any examples really where we're going to play with this at this point, but that's okay. You'll have lots of experience with this form of the derivative in the future. There's one other form of the derivative that comes up occasionally. The book doesn't mention it, but I wanted to make sure that you saw it because people in engineering and in physics particularly use this, especially when it turns out that y is not just a dependent variable, but it may depend on some other variable, time, especially mostly time. So you can think of y as a function of time, and we'll abuse the notation a little bit by doing this, but you can think of y as a function of time, x as a function of time, and we talk about these as parametric equations. You'll see examples of this later. But most often, you'll see physics people or engineering people talk about something called y dot. And this is assumed to be the time derivative of y. So sometimes you might think of this as y prime of t, or dy dt, the derivative of y with respect to time. So all of these would be the same thing. And similarly, x dot would be the time derivative of x, the derivative of x with respect to t. So this is just a notation. I don't think we'll ever use this in this course, but those of you in engineering and physics, I'm sure you will come across this at some point. Okay. Another thing that is brought up in this section, but they don't do very much with it, or at least we're not going to do much with it in the exercises. You will see this again, is if you can take the derivative of a function, could you take the derivative of the derivative? That would be f double prime. And the answer is, well, yeah, of course, why not? If f prime can be thought of as a function all by itself, then sure, you can take this derivative, and this would be called the second derivative. And once you can take the second derivative, then you start thinking, well, what about the third derivative, and the fourth derivative, and so on. This gets a little tedious with all of those primes sitting up there. So instead of writing f triple prime of x, we normally would write, and with any higher powers, any higher derivatives, we would put the number of derivatives that we're taking in parentheses up as an exponent. So this is understood to mean the third derivative. Now, we don't have too many occasions to take third or fourth or fifth derivative, at least not in Calculus 1. But when you get to Calculus 2, you'll see that you're going to take lots and lots and lots of derivatives for a very important reason. Anyway, for now, this is just the notation for the, what you might say, the nth derivative, which means taking derivatives n times. In the Leibniz notation, it's a little bit weird. It would be written d to the nth of y divided by dx to the nth. And we'll talk about this a little later once I have to actually do these derivatives. And at this point, I just want to introduce it to you so that you've seen it at least once before we actually have to do anything with it. All right. So about the last thing we need to talk about, well, no, next to last thing we need to talk about is what does it mean to be, for a function to be differentiable? This is actually very easy. We say that a function is differentiable if the derivative, f prime, exists. So we talk about differentiable at a point A. So that would mean that f prime at A exists. And what does it mean for f prime of A to exist? Well, what does f prime of A mean? Do you remember? What kind of thing is f prime of A? Well, of course, it's a limit. Blah, 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 blah. But it's a limit, and a limit may or may not exist. We've seen lots of examples where the limit does not exist. And in this case, I mean that the limit exists as a real number. So infinity is not a number. So if the limit that we're calculating turns out to be infinite, then we say that the derivative does not exist. So graphically, what would it mean for the derivative not to exist? Well, if you look at a graph, we talked about something like this the other day. What if the graph looks like that, where you have what's called a cusp at this point right here? Well, why doesn't the derivative exist here? Well, if you look at the slopes of lines from the left, if you think of A as being here, and you think of x as approaching A from the left, and calculating these slopes, the lines all seem to be approaching a tangent line that would be something like that. And that would have a slope that's very, very large positive. On the other hand, if your x's are here, the lines that you get are all sloped downwards, and they will increase in absolute value and get steeper and steeper, and they're going to approach something like that, maybe. So as your x comes into a from the right, your slopes are getting, they're all negative and getting larger in absolute value. The other side, they're all positive and getting larger in absolute value. Obviously, they don't converge to a single answer, so there is no limit for a slope in this case. So the limit of the difference quotient does not exist. Now, here's that graph again. There's nothing wrong with the function itself. This function is perfectly continuous. There are no holes in it. It's just that the derivative of this function does not behave itself very nicely. The derivative fails to exist right there. There's no tangent line. Now you might say there's a tangent from the left and there's a tangent from the right, and that'd be true. There is a derivative from the left and the derivative from the right, but those derivatives don't match, and so at this point we say that the derivative fails to exist. Another way that the derivative might fail to exist is when you have a curve that ends up looking like this. It comes to a vertical tangent line, like if you had a circle or a semicircle. If this were half of a circle, on the ends here, your tangent line would be vertical, and there the slope does not exist. Vertical lines do not have slope, so, or they have undefined slopes, so the derivative here fails to exist. So there's a couple of ways that the derivative does not exist. If from one side and from another side you're getting different answers. There are several problems where what you've got to do is construct the derivative from a given function. So what if you had a function like the sine? Let's give ourselves some more room. I'll see if I can draw a decent sine curve here. So the sine would look like this. And if this is the sine, what would the derivative of this look like? Again, those of you who have done this before, just sit on your hands. We're not talking about knowing what the answer is ahead of time as if we had divine inspiration. I want to know how we construct the derivative geometrically. Well, the answer, especially since the problems in the book don't tell you what the formula is, so you can't just rattle off the answer. You're just given a picture. Well, how can you do it from a picture? Well, I suggest you start from the places where there's a horizontal tangent line, because whenever you have a horizontal tangent line, you know what the slope of that is going to be. If this is a horizontal line, the slope of a horizontal line is 0. So the graph of the derivative, we could call this y prime, the derivative of the sine would have to be 0 right here, where the sine goes up to 1, but the important thing is that there's a horizontal tangent line. So at this same point down here, we would have to have a 0 value for the curve. And in fact, everywhere where we have a horizontal tangent line, we're going to have a 0 value for the derivative. Here's another horizontal tangent line right up there, and at that corresponding x on our graph of the derivative, we're going to have a 0. Horizontal tangent line, going to have a 0. Another horizontal tangent line, another 0. Okay, what happens in between? Well, if we start way over here on the far left, looks like all of these points along the curve here as we build up to the peak, they're all positive slopes, but they're decreasing positive, decreasing, 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 decreasing down to 0. So they're positive and decreasing down to 0. So it's probably looking something like that. And then when we turn the corner here, all of the tangent lines are negative and decreasing, 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 more and more negative until finally it turns around and becomes 0. So it's going to be negative, 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 and then turning around and becoming 0. Then the derivatives are positive. Slopes of the tangent lines are all positive, 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 increasing and decreasing back down to 0. So increasing, 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 and decreasing back to 0. And you get the picture. It's going to look like this. So in fact, the people who have taken this before would know that the derivative of sine is cosine. Okay, so let's look at one more example where you might have a picture that might look something like this. And I meant for this to be perfectly straight. Okay, no curves, no curvature to it at all. So just pretend that that's straight. So how would we draw the graph of the derivative of that? Well, if we start at this point, what would the tangents be? They would be negative, slope going down. So here, well, excuse me, not the way we should do this problem. We should start with the places where the derivative is 0. Looks like there's going to be a horizontal tangent line right there. So at this particular point, corresponding to that point, we're going to have a 0 for our derivative. So if this is the function f, we're graphing here the function f prime. And f prime will be 0 right there because you have a horizontal tangent line. On the left, all of these tangent line segments, if I think of them that way, are all sloped down, but they're all negative, therefore, but they get closer to 0. So somehow it's going to look like that. And then when we turn the corner, the slopes go up. So the derivative is positive here. Positive. Now, what's going to happen right here? We've seen this before. This is a cusp. So the derivative is going to fail to exist. So it's going to come to some positive point here, and then all of a sudden, boom, nothing. What about on the other side? What about if x is over here? What's the tangent line to any point here? Well, the tangent line is going to be exactly the same as that segment-like thing, that straight part. So the tangent line is going to be the same here as it is here, as it is here, and it's all sloping down, so it's a negative number. So we're getting the same negative number all along here. Except that right when we get to there, then who knows what it is. It's certainly not going to be here. It's not anywhere. So we can see that the derivative fails to exist because from the left it wants to come up to here, and from the right it wants to come up to there. So the derivative just does not exist. Okay? Well, that should do it for now. See you later.